I'm one of the organizers. I'm happy to, to remind you that the poster session that's after this talk is between 9:30 and 10:40, and we're going to use the Gather Town link. So please attend. It's my pleasure to introduce Dr. Weinan. He's from Princeton University, and he's going to tell us about machine learning and PDEs. Please, Weinan.
Okay, thank you very much, Nadia, for inviting me. When I agreed to participate in this workshop, I didn't realize I was going to be in China. So time difference is a little bit extreme. It's 10 p.m. for me, and I think it's very early for you, and it's 6 a.m. in the West Coast. Okay, so I'll talk about machine learning and PDEs, and two most important issues that I'll be discussing is regularity theory for high-dimensional PDEs, and then PDEs that arise from continuous formulation of machine learning. So let me start. Let's give some very brief introduction to machine learning. So this is the simplest task of machine learning, namely supervised learning. We're given a data set where the label, so-called label, yj at a data point xj, is given by some unknown target function f star. And we want to approximate f star using, for example, neural network models. So this would be example of a two-layer neural network. It's called two-layer because there are two sets of unknown coefficients, aj and wj. Here, sigma is a scalar nonlinear function, usually called activation function. For example, this is the most common choice of sigma. That's called ReLU activation function. So machine learning is really just a set of models. So this will be a model to use this function to approximate f star. And algorithms, for example, gradient descent, stochastic gradient descent, for solving some sort of optimization problem to find optimal parameters, aj and wj. And it's a set of models and algorithms for approximating functions. And it's not just functions. So this is the simplest context in which we're just approximating functions. In unsupervised learning, we sometimes are interested in approximating probability distributions. And for time series, learning time series, the dynamics behind time series, we're interested in approximating dynamical systems. And for reinforcement learning, we're interested in approximating solutions of differential or difference equations. And what makes machine learning, current machine learning, so popular, so exciting, is that this is a particular, it's a set of tools that are particularly effective in high dimensions. So you can think of neural networks as being the replacement of polynomials in high dimensions. So polynomials do not work very well in high dimension. I'm going to explain why. And neural networks are the right replacement. So that's sort of the basic idea. So let me give you some examples of how the success of neural network-based machine learning, deep learning. So this is a typical task in computer vision. We're given a set of images. So this is the CIFAR-10 data set, a very popular, famous data set. And here, we're given a set of images. And each image can be categorized, can be classified into one of the 10 categories. So these images contains either cats or birds and stuff like that. So we're supposed to learn the function which maps each image to its category. So 10 categories, so f star takes 10 discrete values, and each image can be viewed as a point in a 32 by 32 by 3 dimensional space. 32 by 32, that's because the number of pixels. 3, that's the dimension of a color space. So each image is a point from this many dimensional space, this space, to a discrete set of 10 values. So this is learning approximating a high dimensional function. The next example, you see a whole bunch of human faces. And these pictures share one thing in common, namely they're all fake. And what's done here is that from a number of real human faces, we can learn the probability distribution of all human faces. We view that as a random variable in the space of images. So we can approximate that probability distribution sufficiently accurately that we can sample new points from that probability distribution. And these new samples are fake human faces, and that's what you see. And you can see how realistic these images are. So this is the sampling approximating an unknown very high dimensional probability distribution. And this is example is AlphaGo. Many people are familiar with this AlphaGo. And what's important for us is that the optimal strategy for Go actually obeys some Bellman-like equation. So AlphaGo can be viewed as a way of trying to solve this Bellman-like equation. One can solve this equation so well that at least it beats all humans. So these are examples of what machine learning can do, can approximate high dimensional functions, approximate high dimensional probability distributions, and approximate solutions of Bellman equation in a huge space. Now, next, let me talk about PDEs and the regularity theory of PDEs. So regularity theory of, so first the regularity theory of functions. So how do we think about functions, regularity theory of functions? Well, from the viewpoint of approximation theory, regularity is a measure for the complexity of approximating some sort of target functions using simple functions. So the simple functions can be piecewise polynomials, for example. In the classical setting, it is piecewise polynomials. So take piecewise linear function over a regular grid of size h. Then this is a typical theorem in approximation theory, namely the minimum error is bounded by c to the h, c times h alpha to the alpha, where alpha is is a measure of how regular the function u star is. So the C0, which depends on, okay, sorry, let me redo this. Now, classical approximation theory says that a function can be approximated by piecewise piecewise linear functions over a grid of size h with order alpha, if and only if this target function is in the subgroup space of order alpha. So in this particular situation, alpha cannot be more than 2, for example. So subgroup regularity measures how well one can approximate that function by piecewise polynomials, the rate of approximation of that target function by piecewise polynomials. Now, in this particular case, regularity is measured by the subgroup regularity, namely how many derivatives the function has. Now, classical numerical algorithms like finite difference, finite elements, the convergence rate depends on 2 things. One is the order of the method. For example, if we use piecewise linear, piecewise quadratic, we got a different order of method. The order of the accuracy of the method is different. And secondly, the regularity of the solution. So this is the classical numerical analysis. Now, what's important for us is that if we measure accuracy, the error, by the degrees of freedom in the approximation scheme, namely m here. Now m is given by h through this formula. So h is m to the minus 1 over d power. So because of this, if I want to reduce the error to epsilon, to error tolerance epsilon, how big should m be? Well, that's the value of m. Let's take the situation of alpha equal to 1 and epsilon equal to 0.1. Then you get m needs to be 10 to the d. If d is 3072, this is a huge number. So this says that piecewise polynomials is really not very effective for high dimension. It's not just piecewise polynomials. It's also that the way of using Sobolev and Bessel spaces to measure regularity or complexity of functions in high dimensions is not a good idea. So there are increasing evidence that measure a complexity of functions in high dimension by Sobolev regularity is not a good idea because these function classes are just too large. And also grid-based algorithms such as finite difference, finite elements don't work in high dimension.
Weinan, we can't hear you. Are you there? Weinan, are you there?
Yeah, I think it's an internet issue. Let's give it a minute and see.
Can you hear me now? Hello?
Yes, welcome back.
Okay, so you can hear me now?
Yes.
Should I continue?
Yes, please.
Okay. Well, actually, this is the first time I'm experiencing any internet problem. Actually, I've given this talk here before. Okay, anyway, so we want to solve this nonlinear PDE, parabolic PDE, using machine learning. So the first step is to reformulate this PDE as a stochastic optimization problem. It turns out this can be done with the help of backwards stochastic differential equation, a very basic tool in stochastic analysis. So one can show that this problem is equivalent to the following optimization problem, where we optimize the difference between the process y at time t and the given terminal value subject to this set of backwards stochastic differential equation as constraints. As a matter of fact, the connection is that Y is the solution, and Z is the gradient of the solution. So based on this formulation here, one can develop a machine learning-based algorithm in the following way. So first, we discretize in time. We discretize these constraints in time. And then secondly, we approximate this map, this function, U at 0, and these functions, the gradient of U, namely the Z process here at time Tj by neural networks, by different neural networks. And then we got a number of neural networks that we've got a number of parameter sets, and we optimize these parameters by looking at by minimizing this loss function. Okay, so that's roughly how it works. And I know I'm not explaining the details here. You can find the details in these papers. Let me just show you some results. Because the main point of the paper is not explain algorithm, but rather talk about the PDE. Okay, so let's look at this stochastic optimization problem. We have this control here, lambda is a parameter, and m is the control. We want to choose this control to optimize this cost function. So this is the running cost, this is the terminal cost. The Hamilton-Jacobi-Bellman equation for this stochastic control is given by this PDE. And there's an explicit solution using hopeful co-transformation, and that's this. So we can use this formula to calibrate the algorithm we developed using machine learning, and which we call deep BSDE method because it relies on BSDE. So this is the result. The orange line is is to evaluate this explicit formula, and the green line is the solution of the BSDE. The horizontal axis, the lambda. So this is the one example. And the second example is some sort of a nonlinear Black-Scholes equation. By the way, these equations are solved in 100 dimension. So dimensionality is 100. And here too, we're solving some versions of Black-Scholes equation with default risk. And the default risk is modeled by these terms, which are nonlinear. So this is a nonlinear Black-Scholes equation. So these methods apparently has been used to pricing different kinds of options, back-end options, interest rate dependent options, all these different kinds of options. There's a rather active field going on right now of solving PDEs in very high dimensions following this kind of a work. So, but the question we're interested here is the fact that these very high dimensional PDEs can be solved means that these PDEs must have low complexity, even though the solutions are functions in high dimension. So the question is, how can we characterize this low complexity? The intuitive answer is to say, well, these functions, they're low complexity because they can be approximated reasonably easily. The question is, how do we quantify this? Classically, remember, we will quantify this using subleft regularity. To answer that question, we break this question into two parts. One is approximation theory. One is regularity theory of PDEs. So approximation theory is just about functions. Regularity theory is about solutions of PDEs. So let's first look at approximation theory. We would like to prove convergence results of this type, namely, given a set of target functions in some appropriate function space, and this function space needs to be identified, there will be an analog of subleft space. If when we approximate these functions by some neural network models, so HM will be neural network functions, we will get these kinds of error estimates, some subleft-like norm, and some error rate where alpha should be independent of dimension. So that's the main thing. So this is what we expect. And then if we can establish this, then we can ask the next question, namely, given some PDEs, does the solution belong to the right function space? Namely, is the norm, if you think of this as some kind of norm, is the appropriate norm finite for the solution of the PDE? The value of alpha should be half, should be approximately half. And the argument is given here. Namely, if we look at just Monte Carlo sampling in high dimension, the error for Monte Carlo sampling is, variance over m. So here this is the error squared by the square of the error is the variance of the error. So the second moment of the error goes like 1 over m. So that means the error goes like 1 over m to the half. That's why alpha should be half. Now I should remark that using sophisticated sampling, one can improve this a little bit, but the improvement is like scales like 1 over d. So it diminishes as d goes to infinity. So therefore I'm going to neglect them here. So, so this is sort of the analog of what we wanted to have for computing integrals. So what we wanted to have is not just to compute integrals, but rather approximate functions. So this is the kind of estimates we want to look for. So in other words, we want to identify this quantity here. Let me give you an example. So let's look at a simple linear machine learning model, namely a random feature model. So let phi be a collection of random features. So W is a feature vector, which is a random variable. Its distribution is probability distribution is pi. We randomly draw some IID samples from pi, and that's this Wj. And then we form this trial function space or hypothesis space, which is make linear combinations of these random features. Okay, associated with this random feature model, we're going to just use these functions to approximate our target function. So that's the idea. That's called a random feature model. So to state the approximation theory, we need to consider this functional norm. So namely, we need to consider functions which are represented in this form, where remember pi is the probability distribution of W. Of W. So consider a function of this form, and then define the following norm here. Now, this norm might look a little bit strange, but when p equal to 2, this space here, this norm here, and this space here is nothing but the well-known reproducing kernel Hilbert space with this following kernel. So this is the sort of the LP extension of the reproducing kernel Hilbert space. So associated with the random feature models, there's always some, kernel and the associated reproducing kernel Hilbert space. So with that definition of the norm, we can prove the following direct and inverse approximation theorem. Namely, if the infinity norm is finite, then the function can be approximated by random feature models with this kind of error estimate. So this is like, the square, this R, by the way, R is like the square, the L2 norm, the population risk, which would be the weighted L2 norm squared, scales like 1 over m. And then with this is the norm squared here. And conversely, if a function can be approximated by random feature models, and with the coefficients being finite, then that function must be in the right space. Namely, the infinity norm defined earlier must be finite. And well, first of all, it must admit this kind of representation, and the coefficients must be bounded. So these are the direct and inverse approximation theorems for linear random feature model. Now let's look at a nonlinear model, namely a two-layer neural network. Remember, this is the two-layer neural network where the coefficients AJ and WJ are the parameters. So here, first of all, we need to define the analog of the reproducing kernel Hilbert space, the FP we defined previously. So in order to do that, we look at functions which admit this kind of representation. That's a slide extension. And you can see that this is sort of natural in a way, in the sense that it's the continuous analog of this expression. Now, if a function, for functions which admit this kind of representation, we define this norm. Namely, we take some sort of a moments and take the infimum over all such representations. So there are different rows which give rise to the same function f. So we take an infimum over such rows, and these kinds of functions we call Barron function. And the space of functions with finite Barron norm is called Barron space. Now, with this definition, then we can prove analogous direct and inverse approximation theorem. Namely, if a function is in Barron space, then it can be approximated by two-layer neural networks with the expected error rate, convergence rate. And conversely, if a function can be approximated by two-layer neural networks with bounded coefficients, then that function must admit this kind of representation, and the Barron norm must be finite. So this is the analog of direct and inverse approximation theorems. So what we just said is that if we consider for linear random feature models, the right space are these LP extensions of the reproducing kernel Hilbert space. For two-layer neural networks, the right function space is the Barron space. And if you give a different neural network, for example, residual neural network, which I'm going to discuss later, then the right function space is the so-called flow-induced space. So we have a paper on this. And if you consider multi-layer neural networks, for example, 3, 4, 5 layers, then there are evidence that the right space is what is called so-called multi-layer space. Although here, there is still some important issues that needs to be resolved. Anyway, there is some function space defined for multi-layer neural networks. The idea is that these function spaces are naturally associated with these approximation. These are machine learning schemes, just like Sobolev spaces are naturally associated with piecewise polynomial approximations. And with them, one can show these kind of approximation results. So these function spaces are the right spaces in high dimension. So that's the sort of the bottom line of the discussion I just presented. Now the question is, can we establish a regularity theory for this kind of spaces? So this question has not been looked at very much. Let me just mention some initial results. We have a paper which should appear very soon with my postdoc, Stefan Boltowski. We can show in this paper that for heat equations and screen Poisson equations, screen Poisson equation means that the operator is minus Laplace u plus u. So if you just look at Poisson equation, the fundamental solution doesn't decay fast enough. So there are issues at infinity because we're talking about a whole space. So when you need to add this screening term, then the Green's function decays, the fundamental solution decays exponentially fast. So for heat equation and screen Poisson equation in the whole space, we can show that if the right-hand side is in the Barron space, then the solution is also in Barron space. Okay, so so that's one result. And the second result is that if you look at viscous Hamilton-Jacobi equation, the one that I described earlier with square nonlinearity. So this is the one can use Hopf transformation. Then with the help of Hopf transformation, one can show that if the initial condition is in Barron space, then the solution for any fixed time, later time, is in the 4-layer space. Remember these are multi-layer spaces, 4-layer spaces. We cannot show that the solution is in the Barron space. Barron space will be like a 2-layer space, but we can show that the solution is in the 4-layer space. So you can if you approximate the solutions by a 4-layer neural network, then there's no curse of dimensionality. And for Laplace equations on bounded domain, there are counterexamples that even though the right-hand side is the Barron space, the solution is not in any layer space. So I think these are kinds of theorems we'll be looking for for higher dimensions. Namely, we need to think about these function spaces, which are the right objects for high dimensions, and look at regularities of PDEs in high dimensions. And in order to explain why we're able to solve these very high dimensional PDEs. The second part, I want to look at PDEs that arise from continuous formulation of machine learning. So here the idea is that I want to formulate machine learning as a continuous problem, some calculus variation problem and PDE problem. And then we sort of discretize these calculus variation problems and PDE problems to get concrete machine learning algorithms. So in order to do that, the hope is that by doing so, we can treat machine learning as just like PDE. Remember when we do PDE, we first look at where the PDEs were posed, and then we discretize them. That's how we do it. And so here we try to sort of follow the same strategy. But in order to do that, we first need to formulate machine learning as a continuous problem. And the key ingredients for doing that is actually how to represent functions. So for example, we can represent functions by Fourier transform, and that's, A would be the Fourier transform of F. So this is very, it's a very fundamental way of representing functions. But this is not the way to go. So this doesn't work in high dimension. In high dimension, the right representation would be this. And the only difference is that we replace d omega by pi of d omega, where pi is the probability distribution. By doing so, if a function admits this representation, then that function can be represented as an expectation. And then the approximation theory we discussed earlier actually shows that these kinds of functions can be approximated by neural networks with a convergence rate that's independent of dimension. So fundamentally, there are two kinds of representing functions by expectations. The first is this one, very much generalization of this, where I replace e to the I this exponential function by some more general activation function. That would be this. So as we just said, this can be represented as an expectation. We can also lump A and omega into a higher probability distribution, a higher probability space, higher dimensional probability space, and view A as a random variable. So this will be recovered if the distribution for A is delta function centered at AW. Conditional distribution is a delta function. So this would be, formula would be a little bit more a general formulation of this. Or we can consider more general feature functions, not just this form, but rather general feature functions. And then the feature vector will be U, and rho will be some probability distribution of the feature vector U. So these kinds of representations we call integral transform-based representation. There's another way of representing functions, and that's through a dynamical system where the right-hand side has this kind of representation. Consider this dynamical system, and we'll look at the flow map at time one map, and just sum up all the components. Then we get a scalar function. So these, we can also look for representations of some function just through this form. Okay, so now so we're going to use these kinds of functions to approximate our target function. So the problem is formulated as follows. We consider functions, trial functions, which admit this kind of representation with the parameters A and pi, and we use this form to approximate a targeted function f star, and to minimize this so-called population risk. And then we can also, using the terminology of statistical physics, this will be a free energy. And we want to minimize this free energy with respect to the parameters A and pi. And in order to do that, we want to formulate some kind of a gradient flow. Now, borrowing some ideas from a very well-known paper by Halperin and Holmberg in statistical physics, this paper was published in Modern Physics. They say the following: okay, A and pi are two different kinds of order parameters. A is non-conservative, pi is conservative, because pi is a probability distribution, so the total integral must be 1. For non-conservative order parameters, we can just simply take the L2 gradient flow. For conservative order parameters, we need to take a gradient flow as follows. Namely, we first calculate the variation of derivative, which will, in physical terms, this will be the chemical potential. Then we can compute the velocity, and in physics, this will be called the Fick's law. And from the velocity, we can write down this continuity equation. And this will be the gradient flow for pi. And this is nothing but the gradient flow for this free energy under the Wasserstein metric. And one can show, as long as the solution is smooth, the solution, pi, will keep being a probability distribution, namely it's non-negative and a total integral is 1. So by doing so, the machine learning problem becomes solving these PDEs. So now, how do we solve these PDEs? Well, we need to discretize. In order to discretize, we need to discretize R, this functional, and we also discretize the dynamics. To discretize the functional, that's easy. We just use data. Then this becomes the sum. That's the empirical risk. It becomes a sum. To discretize these PDEs, we can use some numerical algorithm. And the most natural algorithm in high dimension is the particle method, because that's the dynamic version of Monte Carlo. And there is also a smooth particle method. For people who are familiar with the fluid dynamics, this will be the analog vortex blob method. And there is also a spectral method. In low dimension, this is very effective. Maybe if the dimension is not so high, spectral method would be natural. So let's take a look at how this works. So let's look at the representation of functions in this form. Okay, and then the gradient flow becomes this. And this is nothing but the mean field model discovered by a whole group of people. May Manasari, and Eric Weinanden, and Giselle Bach. There are several groups of people who independently studied two-layer neural networks from the viewpoint of interacting particles in the mean field regime. And then in the limit, in the hydrodynamic limit, they derive this equation. Also derive this equation. They derive this equation. And you can see this equation can also come very naturally from looking at gradient flow in the space of probability distributions. So now how do we discretize this PDE by particle method? So we're going to replace this probability distribution by this empirical sum, which are delta functions centered at these particles. Then the solving this equation would be like tracking the dynamics of these particles. And the dynamics of these particles are defined in the following way. Namely, if we restrict the population risk into functions of this form. So this function is given rise by the approximation, by this approximation. If the parameters are distributed according to this empirical distribution, then the function represented by these parameters is given this form. And this is nothing but a two-layer neural network. And with this trial function, we can calculate the population risk. Then we would get a function of these that depends on the position of these particles. And then the dynamics of particles would just follow the gradient flow. One can show that this equation and this equation are exactly the same equation if rho is given in this form. So, as we said, this is nothing but the gradient flow for two-layer neural networks. So what do we say? What's shown here is that the gradient flow for two-layer neural networks is nothing but the particle discretization of the continuous mean field model. So, so what kind of results has been proved for this PDE? Well, I would say the most serious result is the following result by Giselle and Bach. And they prove the following: that if the initial condition is it has full support, or in other words, omnidirectional, namely each direction is covered, every direction is covered by the support of this initial distribution. And if the velocity potential converges to some limit, then the global, then the limit must be a global minimizer, namely the population risk must go to 0. Okay, so this result says if there's convergence, then the limit must be a global minimum. So this is a very important result. I think the importance here is that it reveals the fact that initial condition needs to have full support. If we, as we said here, if the initial condition is a delta function, then the solution is just going to be delta function. In this case, many bad things can happen. So this is a bad example. But if the initial condition has full support, then these bad things wouldn't happen as long as there's convergence. So this is a very important result. There are technical assumptions here, which I'm not going to go into. So another result, which I'll show you, this is just look at one-dimensional example, very special situation, and where the target function is given by this kind of representation. So sigma is the ReLU activation function. So in this case, the PDE becomes this form, where the kernel K is defined in the following form. So one can show, in this case, that for the special case when rho star is a uniform distribution, this is a very, very special case, then as long as rho 0 is differentiable, there is convergence. And this is possible because there's an Lyapunov function, and this is relative entropy is the Lyapunov function. In the more general case, when rho star is not necessarily uniform, one can show the following local result. Namely, if the initial condition, if the Fourier transform or Fourier coefficients decays sufficiently fast, and if the initial condition is sufficiently close, then so then one can show that then there is convergence in the Fourier space with a rate which is 1/t. Okay, so this is proved by the usual PDE dynamic system approach, namely you construct, then there is constructed an invariant region. So these are very special situations, but these are the kinds of results that are available for this PDE, which I consider to be an important PDE. Now, I said this PDE is the Weissenstein gradient flow. Now, for Weissenstein gradient flow, the right convexity requirement is the displacement convexity. Unfortunately, for the realistic machine learning models, they're not displacement convex. So the results from optimal transport don't apply directly. And that's why this problem is still quite difficult. So let me finish by looking at a new way of thinking about machine learning from the viewpoint of optimal control. So we're going to cook up trial functions through this dynamical system, where the right-hand side is given by this random feature kind of a model, and the parameter is a one-parameter family of probability distribution over the feature vector. So U is the feature vector, rho tau is a probability distribution for the feature vector U at time tau. And then once we solve this ODE, we add up all the components, we get a function, and we're going to use that function to approximate the population risk. So we're going to minimize the population risk with respect to this one-parameter family of probability distributions. So this is the control problem. One of the most powerful tools in control theory is Pontryagin's maximum principle. And to state that, let's define this Hamiltonian in the state space and in the phase space. So V would be the state, P would be the co-state, and mu here is the parameter, and mu is the probability distribution. And here is the parameter. So this is the extended Hamiltonian. So Pontryagin maximum principle claims that the optimizer, so any optimizer of this control problem, must satisfy the following conditions, namely at each time tau, the optimum control must be maximizing this expected Hamiltonian. And the Z and P are the so-called state and co-states, and they solve this forward and backward equation. So they solve this Hamiltonian system with these kind of boundary conditions. So this is a very well-known result. Now, in machine learning, what people typically do is not this, is to do gradient flow. So we can ask, what will be the natural gradient flow in this case? And the answer is that we just replace this statement here by a gradient flow for the probability distribution rho tau. So we get a one-parameter family of equations. And these equations are all coupled through this forward and backward equation. No, through the function f. Because all these different probability distributions contribute to the same function f. No, through solving this and then this. Okay, now if we discretize this continuous formulation in the simplest way, namely we discretize this ODE by forward Euler, and we discretize these equations by forward and backward Euler, and we discretize this by particle method, we recover nothing but the gradient flow algorithm, the gradient descent algorithm, together with the backpropagation for the residual network, ResNet. This is the most popular deep learning model right now, most successful deep learning model. It's just a so-called residual network. Okay, so this shows that the ResNet's gradient descent algorithm for ResNet can also be recovered very naturally from this kind of a continuous formulation through simplest discretization. But of course, you don't have to do the simplest discretization. You can do a more complicated discretization. I see I'm running over time. Let me just do quickly. You don't have to just do gradient descent. You can develop algorithms, and this is a very important point. You can develop an algorithm based on this maximum principle, and that's this. So this is a maximum principle based algorithm, and it competes very well with the gradient descent algorithm. And that's the maximum principle algorithm is this green line, and these other lines are the stochastic gradient descent algorithms, different version, Adam, Adagrad, SGD, standard SGD, and at least in terms of iterations, maximum principle based algorithm is very competitive. Okay, so the difference, as I said earlier, is that one is doing this, one is doing this. Okay, so let me finish. So what have we really learned from machine learning? Well, actually, it's this kind of representation, representing functions through this kind of expectations. So this is associated with two-layer neural network. This is sort of you can say this is associated with multi-layer neural network, ResNets, residual neural network, and this is associated with the multi-layer neural network. And with this, you can discretize with particle method, spectral method, smooth particle method, or you can view them differently. You don't have to discretize in the way in order to recover the usual neural network models. And then you would give a hope, you can obtain very different machine learning models. Okay, so I would say machine learning provides a new way of approximating functions, and this is a very significant, we have a very significant impact analysis, and there are lots of new PDE problems, both analyzing PDEs in high dimensions and PDEs that arise from machine learning. And here are 3 review articles that can be found in my webpage if you're interested. One is about machine learning theory, one is about high dimensional PDEs, one is about using machine learning to construct physics-based models. So I stopped my talk here. Thank you very much. Sorry for the bug in between. Thank you.
Okay, any questions?
So can I ask a question? So
Sure.
thanks for your talk. So I have a perhaps slightly philosophical question. So, I mean, as you have proved that it's nice that, these like neural network architectures give us a way to approximate these high dimensional things. But on the other hand, as you also pointed out, that the optimization or the convergence of the dynamics becomes really difficult to, even for two-layer neural networks. And so what's your kind of thought on like getting like a posteriori guarantees or like, so like a traditional numerical analysis to say that our algorithm actually results a like approximation that is guaranteed to be accurate?
Okay, so that's difficult right now. But yeah, that's difficult right now. It's not even clear that if we think in terms of training, that Barron space is the right space. So I showed that in terms of approximation theory, Barron space is the right space, but in terms of training algorithm, it's not clear that this is the right space. I think there's evidence that it's not. But that doesn't mean that okay, so theoretically that's hard, but in practice it's very successful. So I would say one approach would be try to do a posteriori, some sort of a posteriori bounds. So there are a posteriori bounds for approximation theory, but they're not the right approach. Posteriori bounds for dynamics has not been sufficiently developed. So I would say that might be a more productive approach to get error bounds.
Okay, thanks.
You're welcome.
Can I also ask maybe a little bit a conceptual question? So first of all, this is really somehow great. It really resonates somehow with an analyst point of view of this and brings clarity to otherwise a field that was not transparent at all. But I would say if one looks at many of the deep learning architectures, then the layers would be of different width and the information would be pulled into this where one thinks to be learning kind of higher order representations. Whereas in your architecture, from if you look at this optimal control point, then all of the layers are of the same width. So do you think that anything is, truly gained by, looking at these pooling layers and bringing the networks to be narrower? And or empirically also, what is that you see with the approach that you're taking?
Okay, so I think there are two, I would give two aspects of the answer here. So first of all, my feeling is that by looking at this optimal control approach, you get rid of the subtleties. So for example, this particular architecture, VGG, particular architecture, maybe not necessary anymore. Now, so going back to the conventional approach, not optimal control approach, conventional approach. So why is a particular architecture particularly better there? Okay, first of all, I don't know the real answer to this question. I can just offer my guess. Mm-hmm. It seems like with multi-layer neural networks, the phase diagram for the error is very complicated. I didn't show this, but if you just look at two-layer neural networks, there's already a phase transition in the phase diagram of the error in terms of the parameters in the network. With multi-layer, it's even more complicated. So it's very important that you choose your architecture to be in the right phase. Otherwise, if your architecture, if the parameters land in the wrong phase, the error will be very bad. So, okay. We haven't looked into this in sufficient detail, but this is my guess. That's what is happening. And that's also saying that these models are too subtle, too sensitive, and we need to develop models that are not so subtle. And the optimal the control theory viewpoint is one way of doing this.
Thanks.
You're welcome.
Question?
Go ahead.
Hi, can you hear me? Can I ask a question, please?
Sure.
Sure.
Thank you. So going back to the first part on the high dimensional Hamilton-Jacobi equations, when you're inputting, when you're using the machine learning algorithm to approximate the function, do you just input the as like a 100-dimensional vector, or is there any pre-processing that's useful to do there?
It doesn't seem to be necessary. So you just put in the initial condition, or terminal condition.
Okay, thank you. That's it.
Mm-hmm.
Are there any more questions?
Let me just ask one. Renan, you.
Hi, Bob.
Hi. You pointed out that there's a big difference between approximations with sort of smooth support and point approximations. But in the machine learning world, you have data, and so everything is point approximations.
Yes.
So this raises the question, more or less it raises the question of how much data do you need to really approximate your probability distributions adequately, or more generally, what do we do about this fact that point approximations are really singular? Any thoughts?
Okay, that's a good question. Unfortunately, I don't have a good answer to this at the moment.
Okay.
No, the answer is no. I'm sorry. So
Yeah.
this is it's not. It's not an easy issue.
Okay. Of course, there's lots of understanding about the quality of approximation of probability distributions by point distributions, but then you're doing a flow method and the points are moving around, so that's a whole different story.
Yeah. Right.
Okay, let's thank the speaker again.
Thank you very much.
Yeah, thank you. So we can move to the informal discussions using the tinyURL link which is shared to the group Zoom chat. And as a reminder, we're going to use GatherTown between 9:30 and 10:40 for the poster session. Thank you.
Am I supposed to go?
I don't know. I guess you are.
Wait, can I ask one more question if you still have 1 minute?
Yeah, sure.
So you mentioned this counterexample with solving the Poisson equation on analysis.
Yeah.
So what is the a more precise statement? Because we are also looking at something similar. I mean, in my group.
You can construct solutions of a Poisson equation on analysis with the boundary condition which in the Barron space, but the solution is not Lipschitz.
The solution is not Lipschitz.
Yeah. So if it's not Lipschitz, it's not in any of the multilinear spaces.
But it does not exclude the approximation, right? So in principle, you can still approximate it in L2 norm. That's in the end of the day what is.
Yeah. You might still approximate well, but it's not in these spaces.
I see. Okay. Yeah. Thanks.
Mm-hmm.
So let me ask you another one. Maybe this is very naive. When you're doing a flow calculation. So you're really trying to approximate the probability distribution, and yet you're moving particles. It brings to mind the fact that when, if think motion by curvature, you really care about the curve, and if you want to get good approximations, you have to distribute your representing points well. So shouldn't there be corrections to the flow algorithms that somehow know that it's the probability distributions and not the particles themselves that matter?
Yeah. And I think this is a very good idea. I mean, if you think about particle filtering, right? In some sense, this is the analog to particle filtering, and there you do need to redistribute. But no one has looked at this yet.
It's not yet being done?
No, I don't think there's anyone who's looked at this. But yes, this is a good idea.
Right.
I mean, in some sense, the birth and death algorithm by Eric Van Eyden and Jean Brunner is kind of version of that, right? So that if a particle carries too much weight, they will split and they will also kill some particles.
That's a little bit different. There you are sort of you're changing the dynamics. Right? You're changing the dynamics. Well, maybe I think you're right. In some sense, maybe.
Okay. Can I just ask a somehow related question? But let's say in the algorithm, right, for the, let's say in the Barron space, that the particle algorithm, you were actually not moving points. You were moving the coefficients that were describing your distribution based on these, ReLU or other kind of basis functions that you were using, right? So basically, is your pipeline then, let's say, if you have just a point cloud to begin with, that then you first approximated, using this Barron space, and then you start your discrete flow. Is that correct? Is my kind of picture correct here?
Sorry, could you say it again? You were broken.
Sorry, right. So yeah, I mean, your discrete flow was in the Barron space, so you were not moving particles as such, but you were moving the coefficients of those functions in the Barron space, correct?
No. Actually, for two-layer neural, it was just a moving particle. That's it.
Okay.
And then there's a more sophisticated version, which is sort of the flow-induced, and then what you say is kind of right.
Because it seems to me that it would make sense to flow in this parameterized set of functions instead of parameterizing the distribution by, by delta masses, right?
That's a discretization.
Yeah. That's what I thought it was happening. I'll take a look at the paper, right? Thanks.
Looks like we're out of questions.
Yes.
Okay.
Yeah. Thanks, Suena, for the great talk.
Yeah.
Thank you.
Thank you.
Indeed.
So Bob and Jianfeng, maybe I'll go to sleep now.